In this video, I'm going to walk you through the process of solving the ALEKS problem called calculating ionic solution composition in equivalence. This problem is going to give you the mass of an ionic compound that's dissolved in a specific amount of water, and it wants you to calculate the concentration of this solution in units of milliequivalents per liter. This isn't a normal unit that we use in chemistry, so this problem might seem pretty intimidating. Let's start by just talking about what that milliequivalent unit represents. So first of all, a milliequivalent is using the metric prefix milli the same way that we would use it associated with any other unit. So a milliequivalent is just 10 to the minus 3 equivalents. And an equivalent is for any, it's a unit of concentration for any ion that's in a solution. You're going to take the number of moles of ion that are in that solution and then multiply it by the absolute value of the charge of that particular ion. So if you're dealing with an ion that has a -2 charge, here you would just be multiplying it by 2, the absolute value of that charge. So for us to calculate the milliequivalents per liter for these ions, we need to figure out how many moles of each ion we have, and we also need to know the charge of that ion. We're going to multiply those two numbers together, and then we're going to convert our equivalents into milliequivalents using this equation. Last but not least, we're going to divide by the volume of the solution in units of liters. This problem is actually not that bad. Just seems kind of intimidating. So for a problem like this, I like to start by writing out an equation that's going to show the dissociation of the ionic compound that we're working with, because it is important that we know not just which ions are present, but we also need to know the charges on those ions, and we need to know the stoichiometric relationship between the original compound. For this problem, the original compound, the ionic compound, is CH3CO2 calcium acetate. We need to know the stoichiometric relationship between that compound and the ions that it dissociates into when it dissolves in solution. So if you're solving this problem, you're probably pretty all right at coming up with this type of equation. If you're not, you definitely are going to want to go back into some of the videos that I have and take a look at how you can identify the individual ions in an ionic compound, because that's definitely a fundamental part of knowing how to solve this problem. And I'm not going to go into that process for this problem because, again, like I said, if you're solving this problem, I think it's pretty safe to assume that you know how to do this step right here. Okay, so again, let's keep our eye on the prize. We're trying to solve for the concentration of the solution in units of milliequivalents per liter, and we do this for each ion in the solution. So that means we're actually going to have two entries into this ALEKS problem. It does give us an option to add rows. We're going to need to do that. We're going to put each ion on its individual row because we want to calculate the milliequivalents per liter of the calcium ions, and we're also going to calculate the milliequivalents per liter of the acetate ions, both. And how are we going to come up with that? We're going to begin by figuring out the milliequivalents for each ion. The milliequivalents are just 10 to the minus 3 equivalents, and the equivalents are the number of moles of the ion multiplied by its charge. Now the charge is right there for us, it's pretty easy to see, so we need to figure out how many moles we have of each one of these ions. ALEKS tells us the mass of the original ionic compound. I'm just going to make a note of that down here. It is 1.75 grams. And what we want to do is convert that mass, 1.75 grams, convert that mass into moles. Once we know how many moles of our original compound is, we can then figure out, we can use the stoichiometric relationship to figure out how many moles we have of calcium and also how many moles we have of acetate. I went ahead and looked up the molar mass of calcium acetate before I started solving this problem. I do want to warn you, ALEKS is not going to like it if you just use a rounded molar mass for anything. So make sure that when you solve this problem, you are using the whole entire molar mass for whatever compound you've been given. I am going to do the gram to mole conversion down here for the calcium acetate. 1 mole is 158 grams, and that is going to give me 0.0111 moles of calcium acetate. Now again, always trying to remember what is even the point of this. We're trying to calculate the milliequivalents per liter. We're starting by trying to figure out the milliequivalents. The milliequivalents are given to us by this equation right here. We need to know the number of moles of each one of these ions. So we can see that we start with 0.011 moles of calcium acetate. In terms of the calcium ion, there's a 1-to-1 molar relationship between calcium acetate and calcium. So that means for every 0.0111 moles of calcium acetate, we are going to get 0.0111 moles of calcium. And then also we have this 1-to-2 relationship with the calcium acetate and acetate. So for every 0.0111 moles of calcium acetate, we're going to make 0.0222 moles of the acetate ion. We are, again, keep our eye on the prize. We're trying to calculate the milliequivalents per liter, and right now we're working on the milliequivalents part. The milliequivalents, the equivalence is going to be the number of moles of the ion. We've got that figured out, multiplied by the absolute value of the charge of that ion. So for calcium, the charge is 2. And so that means that the equivalent of the calcium ion is 0.0222. Actually, I'm going to write the unit at the end of the number. And then for the acetate, the charge is a 1. So the equivalent for the acetate ion is 0.0222 equivalents. Now, it is pretty normal for the equivalence of your cation to be exactly equal to the equivalence of the anion. That's going to be the usual situation. Most of the time, that's how it's going to work out. And so that means when it's time for us to calculate the milliequivalent of the cation and the anion, again, we're going to get the same number. And also when it's time to calculate the milliequivalents per liter, again, we're going to get the same number because we're starting with the same number of equivalents. So for the remainder, I'm just going to carry out the math only on just the 0.0222 number, and we're going to remember that these two have the exact same equivalent, which means they'll have the same milliequivalent, which means they'll have the same milliequivalent per liter. So let's go ahead and convert these equivalents into milliequivalents. 1 milliequivalent is 10, that's a funny Q, is 10 to the minus 3 equivalents. So that is going to be, let's see, I need to multiply by 2 and then divide by 10 to the minus 3. Which gives me 22.2 milliequivalents. And the problem is asking for milliequivalents per liter. So now I'm going to take that volume of water, I'm going to convert that into units of liters. That's going to be 0.09 liters. And that's going to give me 246 milliequivalents per liter. And that is, again, that is the same for both the calcium and the acetate. Now, in terms of putting this answer into ALEKS, it says here that it wants you to calculate the concentration of each ion and write the concentration in the second column of each row. It does say list only one ion per row. So I guess I should start the instructions up here. List the chemical symbols, including charge of each ion. List one ion per row. So we're going to start with our first ion, calcium 2+, and the milliequivalent for that is 246. And then we're going to need to click on this add row button so that we'll get a second row in here where we can write our second ion. And I'm not sure why ALEKS isn't just giving us enough rows to begin with. And this one, we would write the formula of the second ion, the acetate CH3CO2-. And we're just writing the formula. We're not saying anything about the fact that there's 2 of them in this solution. And then we're going to write the milliequivalents for that again. To the correct number of sig figs. For my problem, it's going to be 3. And there you go.